So let's talk a little bit about section 2 here in chapter 17, part 2. We talked earlier that enthalpy change is delta H, and so delta H is the change in enthalpy or the change in heat, so the amount of heat produced or the amount of heat that is absorbed. And if we write it in a chemical equation, we can write it both either as a reactant or a product. So here in this example, calcium oxide is one of the main components of cement. So when calcium oxide and you add water to cement, it produces calcium hydroxide, and it also produces 65.2 kilojoules of energy. So this is an exothermic reaction, and you can see that the energy amount is written as a product. So the enthalpy change is considered a product. So any kind of a chemical equation, a balanced equation that shows the enthalpy change or the change in heat is called a thermochemical equation. So if I looked at total amount of energy or total amount of enthalpy on a scale here, so if we have the amount of enthalpy here's the amount of enthalpy of here's the reactants and here's the products, we can see that the total amount of reactants is higher than products, so we lost this much energy. So either write it as a product or that the delta H is negative. This is called the heat of reaction. So the enthalpy change is called the heat of reaction, and it's written always as a delta H to show exactly as it's written. So from reactants to products in the forward direction, we call it what is the delta H. You must also always have the state of all reactants and products because it does matter. And we would also understand that when we give delta H, it's under what was called standard conditions, 1 atmosphere and 25 degrees Celsius. Now that's not the same as STP for gases, which is 1 atmosphere and 0 Celsius. So a little different there. Basically it's room temperature, 25 Celsius. So for heats of reaction, we understand that it is related to the molar amounts or the mole ratios. So for every 1 mole of calcium oxide, I get 65.2 kilojoules of heat. So we notice the delta H is negative because the energy of the reactants is higher than the energy of the products. For an endothermic reaction, we get exactly the opposite. Here we can either write that the 85 kilojoules of energy is added as a reactant, or we can say that the change in enthalpy is a positive 85 kilojoules. So the sodium bicarbonate, the baking soda, the reactants have this much energy, whereas the products have a higher amount of energy because the energy was put in, because it's an endothermic reaction. So then the carbon dioxide release is, what causes our muffins to, be beautiful. So a thermochemical reaction can be written either way. It can be written with the energy as either a reactant or product, or with the delta H off to the side. And if the delta H is off to the side, the sign matters. Positive for endothermic, negative for exothermic. So we look at the mole ratio to determine the total amount of heat absorbed or released. If I have it says 2 moles of sodium bicarbonate requires 85 kilojoules of heat. So if I had 4 moles, I would need twice as much. So it's based on that kind of mole ratio of how much we've got. Here, this slide emphasizes why the physical state must be given, because the here's decomposition of water. So here we have liquid water turning into hydrogen and oxygen gas, or we have gaseous water turning into hydrogen and oxygen gas. Notice that it takes more energy to get the liquid reaction to happen than the one where we start with gases. So that's the difference. On an interesting side note, to vaporize 1 mole of liquid water to water vapor requires exactly 44 kilojoules of energy. The difference in these two reactions between the liquid and the gas is 44 kilojoules of energy. So what you have to do is this liquid has to first actually be converted to the gas using that 44 kilojoules of energy before you can break it down into its components. So here we can use the enthalpy change to determine total amount of heat required. So if I had 2.24 moles of the sodium bicarbonate, we could use a ratio that it takes 85 kilojoules for every 2 moles. Where'd I get that? Here and here. So 85 kilojoules for every 2 moles. So then we come up with 95.2 kilojoules as far as the number of moles, amount of heat required. The last part here is heat of combustion. And heat of combustion is just a term to mean the heat of the reaction if we're burning. So it's the same as heat of reaction, only we're burning it. So for example, natural gas, the burning of natural gas, which is also called methane, is balanced equation here. It says I also produce 890 kilojoules. So the balanced equation says 1 mole of methane releases 890 kilojoules of heat. So if I wrote that as the enthalpy, or delta H, that would be a negative 890 because it is an exothermic reaction. So this is a table that shows the heat of combustion for some different substances. So it's a relative amount of the amount of energy stored, because the amount of energy released. So it is all carried out at standard conditions, and this is kilojoules per mole. So the amount of energy stored in octane, which is a major component of your gasoline, is actually less than the energy stored in the bonds of sucrose. I think that's kind of interesting. You know, that the glucose and sucrose, the sugars, store just as much, if not more, energy per mole than the fuels that we burn for our cars. So the fuel we burn for our bodies is actually contains more energy than the fuel we burn for our cars.